So today we will talk about the maths of diffraction. We saw in the last lecture, in the last video, how the principle of superposition and the fact that we measure intensities, so we square the amplitudes, leads naturally and automatically to the concept of interference. And so we actually now have all the tools to see what happens if light comes from an object, it goes through the microscope, is processed, and then it is thrown onto a screen, i.e. a camera screen, for example, a CCD chip, or your retina. And so to understand what the field is, the electric field, and the intensity pattern that we actually record with our recording devices, we just have to take the light coming from every point in the object and trace it to the point where it lands on the image plane, and we add up all the correct phases from all those waves to give us the overall pattern. And the integral we need to solve to do this is called the diffraction integral. And the condition of diffraction that applies to imaging instruments is Fraunhofer diffraction. And this is what we will look at now in this video and in this lecture. And so we begin, if I switch back now to the notes, by trying to understand how we might achieve this summation of phases. Okay, so here it finally comes, diffraction. And so to consider what happens, let's just first look at this picture here. In this picture you have a light source, S, which is a point. So this point throws spherical waves out into space, and then a long distance away, these spherical waves hit an aperture. So you see this opening here in a screen. And so, of course, by Huygens now, each point in the aperture acts as an emitter of secondary spherical waves. These spherical waves travel out in space, and then if I look at any point in space, let's say this point P in space, all I have to do is I have to take the spherical wave that arrives from this little element in the aperture, and I have to know what the amplitude and phase is at this point, and then I take any other point from here, I go up, and here's a spherical wave emitted from that point, and of course I need to add the phases and the amplitudes correctly from all the openings inside the aperture. Now, in the case that this point source here is a long way back from this aperture, then of course the spherical waves arriving here, so the spherical waves are coming in here, they'll be so far away that essentially the phase, if this distance here is much larger than the wavelength of light, which it usually is, then the phases inside this aperture can be approximated to be plane. So there will be hardly a phase difference between those. The alternative is, and perhaps that's the situation that we will from now on look at, is to just illuminate this aperture with a plane wave, and in that case the phases inside the aperture are all constant. So it doesn't matter whether you're looking at this point in the aperture or in that point, the phase offsets of the light leaving these points towards the point you're looking at in space, or any point in space, the phase offset is 0, right? And because so this is actually the situation that we encounter later when we discuss the microscope. So just to bring these points home, we need to just at the phases at any point in space we wish to look at on the screen. So this is one point. Of course, we have to do this with all points on a screen or a camera chip or the retina, whatever it is, to get the right intensity pattern, of course, later on. So we do this for the fields first, then we get the intensity, and that gives rise to the diffraction integral. So the integral we solve is called the Kirchhoff diffraction integral. And so I'll just draw this situation again, so we see how it works. So if I have an aperture, so here's an opening, and so I have a plane wave now. So we said either a spherical wave coming from a source a long way away, or even better, just illuminate this with a plane wave, so the phases are constant. So that hits the aperture and the light goes through. And let's now draw coordinates like this. Let's make this y, and let's make this x, little x. And let's now look at an arbitrary point on my camera chip. Let's say I look at this point P here. Okay, so P may have coordinates big Y now, and big X. And so of course the phases inside the aperture of the fields are all constant because we have a plane wave illumination. So then let's look at a small element inside the aperture like this. That, if it's small enough, emits a spherical wave. And so let's see, it leaves towards P. So if I draw an array of light going this direction, then I have spherical waves. The distance here is RP. And so what we have, so we add up all these little spherical waves from all points. I mean, there will be another one leaving in this direction. Of course, it will have a different, the phase now will from this element here, will because it travels a different distance, then they will arrive with different phases, right, at this point. And so that's what we need to take into account and integrate over all these little fields. So it's actually now easy to see what this looks like. The amplitude E at point P is given by, I'm just writing this down, it's a double integral because this is we have to integrate over this area here, E of x y times e to the I k rp divided by rp dx dy. And so if this is the aperture A, we integrate over the entire aperture A. So there's a couple of things you notice. This here is a spherical wave. We have ignored the omega t term in there. It's not important. You can take it actually, it's because we're assuming just one frequency, it will be the same for all the spherical waves coming here. So this one will have the same frequency and same wavelength. It will just go in a different direction towards this point, right? So the only thing that changes is this RP will be different here. It's longer here, and this one is shorter. And then the all-important point is this phase term here, 2 pi over lambda times RP. K is 2 pi over lambda, wave vector times RP. And of course, it tells you how often does this wave cycle between maximum, minimum, maximum, minimum, maximum, minimum until it arrives at point P, and the same for this one. And of course, tiny tiny path differences because the wavelength is so small. It's 500 nanometers, half a micron. So if the difference in path is just half a micron or less, right, that will lead to positive or negative, constructive or destructive interference at that point. So the point could be either bright or small, depending on this, on these phase differences. This is the amplitude at point x and y. So the amplitude here, the amplitude there. So usually that's a constant. I mean, so E at x, y is often the aperture is evenly illuminated, but we'll look at that in more detail later on. But of course, the aperture may have arbitrary dimensions, so we have to actually integrate over the shape of this aperture. And you do this in Cartesian coordinates by integrating over dx by dy. And there's a couple of important assumptions. I mean, actually, this RP, you remember where that comes from in the spherical wave. That is because as the spherical wave emanates, the flux through an area of the light wave in space will decrease because, you have a bigger shell as you go further away from the point source, right? So as the shell increases, the actual flux decreases, and you took that into account by this 1 over RP term. Now, in fact, there is, of course, a longer path going from down here than it is from going up here, but actually, usually, this RP for RP much greater than lambda, which it always is in our applications. You can take that 1 over RP term to be constant. 1 over RP is approximately constant. So you can take that out of the integral. You can take that out of the integral, right? It's a constant, and actually it's only this term that remains important. But don't make the mistake of treating the RP constant here. The reason is that here, the 2 pi over lambda term, the lambda is so small, and the wave is oscillating so quickly that even minute differences, whilst they do not have much effect on the amplitude, right, that arrives here, they do have an enormous effect on the phase. Because tiny differences in paths lead to large phase differences, but they don't lead to large amplitude differences. That's why we can treat this as constant, but we have to explicitly include it in this phase term up here. There are 2 more terms which, for the purpose of this course, you can ignore. These are advanced. The derivation of this diffraction integral is actually quite complicated. It is from a topic called scalar field theory. You can see why it makes sense, but a complete derivation requires the inclusion of these terms in here. But the I factor here is essentially something that takes into account that the wave only propagates in the forward direction, because a normal spherical wave would of course go into all directions, but here we only look at the forward field for these secondary waves, and there's also a phase term in there with the I that comes in. But you really, for the purpose of course, this front piece here is completely unimportant to us, because if we take the intensity and so we multiply this with the complex conjugate, this term just turns into a constant, a real constant, and so we are not really interested in absolute values, right? So we can just ignore this for the purpose of our calculations. So the assumptions are that we illuminate with plane waves, and the other is that the RP is large with respect to aperture dimensions. If that's the case, then this certainly holds what we say with this in this case. And in that case, we can just rewrite this equation. E of p is proportional to the integral over the aperture E of x, y, e to the I k rp dx dy. And this is a really important result. This is at the heart of this course. And we'll now go through a few examples to see how this works in practice. So the next part I want to discuss is that, so I hope you've seen this. Just to repeat this again, in case I didn't hold the paper up enough, just to repeat this, we have treated this as constant because we're not interested in the end. We always take the intensity, so we square. So we're only interested into the proportionality factor. It's an integral over the aperture in x and y, and we are summing all the phases e to the I k r p that arrive at that point p. Okay, so the next thing I want to discuss is if so we've got this equation here again. E of p is proportional to E of xy, e to the I k r p dx dy. So the conditions we've just said, rp very large compared to the aperture dimension, plane wave arriving at the aperture. These conditions are called Fraunhofer diffraction conditions. And it is now worth stating in more detail. So this integral holds when the phase fronts are parallel in the aperture. And it also holds when the paths leaving xy for p are parallel. So that would be strictly what Fraunhofer means. So, I mean, of course, in this diagram, this and this path and this path they are not, I mean, the way I've shown it, they certainly don't look to be parallel, right? But if you imagine that rp is a very, very long distance away, then of course this will approximate. So for rp being much larger than the aperture dimensions, then this is a good approximation. And in fact, we can, in a microscope, make this approximation perfect. And I will show you how. In fact, the reason why it is perfect in the microscope is because we're dealing with a 4F imaging system. In this case, the Fraunhofer conditions are exactly upheld. So the way to achieve this is in a microscope. And so if I draw this, first of all, let me just show you one way to achieve Fraunhofer. If I have a slit that looks like this, I have a plane wave coming onto the slit, and so Fraunhofer says I consider spherical waves from inside the aperture that leave towards a point. So we only look at the phases arriving from rays that are parallel. Of course, these will never meet except at infinity, right? So if we really want to just look at parallel rays that come out, what you can do is you put a lens here. If I put a lens here, and I look one focal distance behind this lens, then you remember what a lens does. It will take all rays, all parallel rays will be focused to the same point. So if I put now my camera screen or in this plane here, then if I draw a central ray, this angle will be focused to this position. And of course, all of those will be refracted to this position. Okay? Because that's exactly what a lens does. And so, and it preserves all the phases. So if this had a certain phase, the phases are preserved as if, you know, as if you were looking, as if you're looking at comparing the two parallel rays, the phases of the two parallel rays directly, right? That's the ingenious thing of what a lens does. It focuses light rays. The lens focuses light traveling along parallel rays, preserving phase differences. So in practice, these Fraunhofer conditions you could achieve by, if I go back to the previous thing, you could achieve Fraunhofer conditions either by putting no lens there, but then going with the screen a long way back, and then they become almost parallel, these different rays coming towards P. Or even better, you put a lens in there, and you just really then bundle only the parallel rays at the different angles. So if that's F, and if that is theta, then this distance here will be just F times theta. So it will collect all these different angles theta and focus them to a particular point P on the screen. And there we have it. So that will give you, that will ensure that we are, that the light arriving from the aperture at any point on the screen will be that collected from parallel rays. Okay, and this allows us now to, so we can now actually take this a little bit further. If I want to make a system and I really want to achieve Fraunhofer diffractions, so I want plane waves in my aperture. So to illuminate with plane waves, that was the other conditions. What you can do is you can take a point source S that emits spherical waves. You put it one focal distance away from an illumination lens. The light then, the spherical wave is turned into a parallel wave. The parallel light waves illuminates the aperture. And then you have a collection lens afterwards. And one focal distance away, you put the screen and you get the diffraction pattern according to Fraunhofer conditions. Now, if you have this two-lens system like that, and so essentially what you get here is the diffraction pattern corresponding to this aperture here. And this looks very close to the microscope. Because what this is a 4F system. So you could have F, 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 F. The distance here doesn't really matter so much. We remember this infinity space thing. But certainly the 4F system, as we had it, F, 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 so this is the tube lens, and this is the objective lens. That certainly, what you get here would be Fraunhofer diffraction from this point. So this point is spherical waves, you get parallel waves, and then they get focused down to this point again. And what you end up here is diffraction of the aperture. We can now use this to describe what the diffraction is from a series of apertures. And the simplest one to discuss is an infinite slit. So essentially what you have is we make a very small slit, so that the slit becomes small, we get diffraction. You remember, as the more diffraction, the smaller the slit gets, right? But it's infinitely long in this direction, so there's no diffraction in this direction because it's not, the light isn't restricted in any way, right? It's only when you really make it small that you are playing with the light field, and the spherical waves that are emanating will give you summations that don't look like what you had before the aperture, right? So here's my slit, and if the width of the slit is b, in this direction here, then I can draw this as follows. So I have a slit that has just a single slit. Looks like this, and this is at b over 2. This is at minus b over 2. That's the slit width is b, and so now what I do is I use Fraunhofer conditions. So I put a lens in here to collect all the parallel rays, leaving the aperture. I have a plane illumination here from the left onto the aperture, and I now draw in. I want to know now. Let's draw in this angle. So this is R0, and it will go. Let me see where that would end. If I have my screen somewhere around here, I put the screen here. Put the screen here. Let's have a look. And so this is a distance f after this lens. And then we can find out where this ray would land. This ray would land wherever, if I take a central ray that is parallel with this one, so it would land somewhere around here. Okay. So if that is theta here, then this is also theta. So it will collect all rays with angle theta, all parallel rays, and put them onto this point. So this will land here. And similarly, if I look somewhere up here, that is a parallel ray to this, emitting another spherical wave. Actually, that may be just exactly as it happens. This one is the central ray, just by coincidence, the way I've drawn it. But of course, this will be true for any other ray that leaves in this direction. It will go up to, if it's with any ray with angle theta with respect to the central to this ray here, starting from the center of the aperture. So that angle theta then also appears here, as you can see. So this angle theta is also here, and this is the path difference between these two rays, which are y sine theta. So y is in this direction here. So if this is position y, let me just draw this in. So this here is y. At distance y from the center here up, there's a path difference between these parallel rays leaving for the screen, which are y sine theta. Okay? And they appear on the point P here, where the position is f times theta. That's the way a lens works, right? And so we say our 0 is here, the 0 y, so we have y in this direction, right? So y goes in this direction. And so, in fact, we are only looking, we're only doing the integral, the diffraction integral along the thin dimension, because along the large dimension, you don't have to do it. There's no diffraction in this thing. So it becomes a one-dimensional problem. So it's only along the dimension where we really get significant effects. If the dimensions are much larger than the wavelength of light, then of course there is no diffraction, as we've seen in the first lecture. So can we do this integral then, the Kirchhoff integral for this? So we have E of P is proportional, so we integrate from minus b over 2 2b over 2. And we now take the field, because it's a one-dimensional problem, we only have one integral, we don't have to bother to take the long direction here along x. It's proportional to the amplitude at each position y times e to the ik r naught plus y sine theta. Okay, so r naught is the ray that leaves from the center. So its phase is ik r naught when it arrives at P. And any other ray will have an extra bit added in, or an extra phase lead or phase lag of y sine theta, whatever y is. That can of course be negative, so it can be a phase lead or it can be a phase lag. So this one travels extra, so it accumulates extra phase, and so that is taken into account for by multiplying 2 pi over lambda times y sine theta and adding that in. Okay, and then we add that, then we integrate with respect to y, and so you can see that this part here, this part is constant, right? So we can take it out of the integral, because ik r naught is just the same for all of those, right? It's just that y sine theta term that changes. This term, the amplitude inside, if you have a plane wave like this, is also constant. So we can also take that out of the integral. And so we end up with an integral of e to the ik y sine theta dy. And so that becomes c times e to the ik y sine theta between minus b over 2 and b over 2 divided by ik sine theta. So the integral of e to the ik y sine theta is equal to ik y sine theta divided by ik sine theta. Okay, and so that is equal to, so if we take some of these constants out again, so we can rewrite this. This turns out to be c dashed, and I leave this up to you, 2i sine, but you may be able to see why that's the case. You remember that e to the I theta, or e to the I anything, it can be written as a complex number a plus ib, right, where the real part is I sine theta, and the imaginary part is I sine theta, and the real part is cos theta, right? Now the cos terms, cos b over 2 is the same as cos minus b over 2. So that means the cos terms will be 0, but of course sine a and sine b over 2 and sine minus b over 2, they have opposite signs, and so that will mean that the sine terms remain. So you end up with 2i sine k sine b over 2. Hang on, sorry. K sine theta. Let me just rewrite that. Is equal to c times 2i sine of k sine theta times b over 2 over ik sine theta b over 2, and so we can take these all out, and you then see that e of p, this looks like a sinc function, is proportional to sine beta over beta is equal to sinc beta, where beta is equal to half k b sine theta. Okay, so you see that what that means. So there will be the sinc, of course, has a function. The sinc, let me just look at this again. So if I plot this function, if I plot this sinc function as a function of beta, so you could have at 0, so we have, if I plot it as a function of beta, then you get pi minus pi. It will look something like that. Yeah, something like this. And so we plot the intensity I over I naught. So this is the intensity inside the slit. So that's equal to 1. So I naught will be E squared, whatever E was inside the slit. So we just normalize that so that that's equal to 1. And then you get a first minimum when beta. So, and I should just say E, the intensity I is equal to E of P squared, i.e. that times the complex conjugate, which is just sinc squared essentially. So that's what the sinc squared looks like this. It has a minimum intensity here, and so at this angle here, when kb sine theta is equal to pi, it goes to 0. So we can write this. So we can say first 0 when half kb sine theta equals plus or minus pi, or I mean, so for small theta, sine theta is equal to theta, and that is then equal to plus or minus 2 pi over kb. Okay, and so again, I now urge you to try and understand what you expect would happen when you make B, the slit width, smaller. So obviously the sinc pattern will change shape, and so the smaller you make the slit, the wider the sinc pattern becomes, and you can probably, I want you to understand why that happens. Just like we did in young slits, when you have the two sources and you take them further apart, the pattern becomes narrower, and if you put them further together, the pattern becomes further apart. And it's the same thing here. And so the actual position, these minima appear at positions on the screen f2 pi kb. So at these angles. At these angles, you get minima of the pattern. So you might, so what you see is something like that on here, and the minima appear at f2 pi over kb. Yeah. So I would just like to finish this part by just pointing out one more thing to you, because for those who've done Fourier transforms, you will notice something, and that is that that if you write this equation, if I go back, if you look at this equation here, this Fraunhofer equation, so if you look at this equation here, E of p is equal to E of xy, E3 ikrp dx dy. So for the slit, we had E of p is, sorry, if I go back to the slit equation, so I look at this equation here. So we said we only have to consider E of y times E3 iky sine theta. Then if I do this, E of p is proportional to integral E of y e to the I k y sine theta dy. If I rewrite this as E of y e to the I v y dy, where v equals k sine theta, then some of you may recognize this as the Fourier transform of E of y. So this is remarkable, in fact, because if I take this parameter here, k sine theta equals v, and write this equation like that, then you can see that E of y and E of p are a Fourier transform pair. In other words, the aperture function will be Fourier transformed in the image space, and the diffraction pattern that you get on under Fraunhofer conditions turns out to be exactly the Fourier transform of the aperture function. And of course, a rectangular slit, the rectangle function, for those who know, we will go into this in the next lecture, but for those who know, the Fourier transform of a rectangle is of course a sinc function. And that's precisely what we worked out by going through the math. But now, by noticing this, you recognize that under Fraunhofer conditions, the images that you form with the tube lens are essentially the Fourier transforms of the aperture functions that you image. Okay, so with that, I would like to finish. I would like to finish this particular part, and I just show you a little experiment. Thank you.